Let me give a few examples on the GPU. So on the GPU, picking good algorithms really means picking algorithms that are fundamentally parallel. And my favorite example of this is related to the example I gave for the CPU, where I compared merge sort, which is order n log n, with insertion sort, which is order n squared. Now, in fact, most CPU algorithms texts would probably tell you that heap sort, which is also order n log n, is a better choice than either of these. It tends to run a little better on the CPU. But it turns out that heap sort is all about updating this shared data structure called the heap, and that's a very hard thing to do in parallel. And so, in practice, a merge sort is a much better choice on a parallel machine like the GPU. In terms of basic principles for efficiency, we've already discussed some of these. A big one is coalescing global memory accesses, and another is using shared memory, which is faster, for frequently accessed data within a thread block. We'll just touch on a few GPU Ninja topics like optimizing bank conflicts and shared memory, and optimizing the use of registers. And I've certainly seen my share of sort of GPU bit twiddling micro-optimization. One example that comes to mind is the use of floating point denorms in order to abuse the floating point arithmetic units for additional integer math performance. And this kind of stuff is just firmly in the Ninja category. You know, it's almost never worth the time or the code obfuscation that results, and we won't be talking about them at all today.